Hello everyone, welcome to Mydbops Open Source Database Meetup 15 recorded live in Bangalore. Mydbops excels in open source database management, offering tailored solutions for MySQL, Postgres, MongoDB, TiDB, Cassandra and more. We organize meetups to facilitate knowledge sharing, networking and collaboration among professionals in the field of open source database management. And coming back to the recording, Mydbops was thrilled to present Shivji Jha from Nutanix Cloud Platforms discussing modern database complexities. Shivji dived into the evolution of transactions, challenges in implementation, and insights into distributed database environments. This session offers valuable insights for anyone interested in database management. Without further ado, let's dive into the recording of Shivji's insightful presentation.
Okay. So I think I've already been introduced. So I'll skip the boring stuff mostly. But I have a keen interest in databases, streaming systems, and application architecture. Like the gentleman introduced, I have been sort of working for a decade. My first job was at mysql. That's where I developed this keen interest in exploring database internals. And the interest has carried through over the years. And then a result of that is sort of these talks that I do these days, just to have my knowledge challenged. Otherwise, you feel like you know a lot. And then you come to such a meetup, people ask questions, and they're like, man, fine. So that's the idea. What I am trying to do here is basically put some of my thoughts, and I am expecting some conversations, some questions where I am challenged as well, right? So, and then I'll hopefully be able to take some, and then for some others I can get back if I can't answer those questions. But I've done a lot of preparation for this, pretty much 2 weeks, spending a lot of nights for this. But coming back, I love open source software. If you have followed me a bit, I spend a lot of time reading open source code, contributing, getting to conferences and meetups, giving talks, just listening to people, a lot of people. This is my external talk number 23, and I work as a staff engineer at Nutanix in the data platform team. So this is sort of also related to my job. It's not like I do this on the side as an interest only. The trick is to make your interest your work, right? That's how you get deeper into it. Finally, coming to the talk, we will look a bit on transactions, and we will explore a bit of history. So lately, I have been sort of reading some history books and everything. So I thought, let's start the story with some history. And then while you talk transactions, how can you not talk ACID, right? But I'll keep it very brief. I will mostly run through it quickly so that we can get to the heart of the talk, which is implementing transactions in different databases. What are the trade-offs and stuff? How do you do that on one server? How do you do that across servers in a distributed setting, which is where it gets really complicated. And finally, we will go from theory to practice. And to see the transactions in action, we will pick some really huge databases in the cloud infrastructure today, the modern infrastructures, and look at how they implement transactions internally. And you will see that I picked 3 databases that run on huge scales, and they do implement their transactions in very, very different ways, right? The point is, at the end of the day, it's all about design trade-offs. What is your app looking for? And depending on that, you will see how these databases, depending on what they are trying to guarantee in terms of transactions, their implementations are actually quite different. So let's begin the story. So transactions, right? Like I said, a historical perspective first. So almost all the relational databases, and lately even some NoSQL databases, have started supporting transactions. Like DynamoDB, I think, only last year announced transactions, if I'm right there. So the first system was, actually, it might surprise you, in 1975. That's when this system R was released by IBM. And from then, transactions have been there. So it's a long history over more than 45 years now, right? Kind of nice thing is that across all these 45 plus years, the general understanding about what transactions are have remained quite sort of similar, right? And if you look at the systems today, the popular ones, MySQL, Postgres, Oracle, SQL Server, all these transaction or relational databases, they have pretty similar transaction semantics if you look at it from the top at least, right? Implementations might differ a bit, but and they are surprisingly similar to the first system of system R. Sort of taking some leap ahead, around late 2000s, a decade ago, there was this huge NoSQL wave. Now you have the AI wave. Like everybody is talking AI. If you put an AI, maybe 10 more people would have come by now, right? but then there was this whole NoSQL wave. I think, in my opinion, now it has settled down more, where people understand that there is place for all the different kinds of databases. And if you look at the beginning, the NoSQL camp used to say, you know what, because of these transactions, you can't have high performance and availability. So we will forego transactions. We will sacrifice that to get nice sort of query languages and easy to use and whatnot. That was the way MongoDB came to the scene, and it's pretty good. It's been nice. While on the other camp, SQL camp, people, and I was one of them, I was employed by MySQL at that point of time. I used to work with the replication source code there. So we were under the impression that, you know what, this is not serious databases. If you really care about your application, if you're serious about getting some useful value out of your data, then you got to use SQL, right? Turns out, time has a way to show the right things. Both the camps were exaggerated, in my opinion. And it's all about trade-offs, like I said, right? Moving over to ACID. I don't think we need to introduce ACID too much. That'll probably bore people. But I'll quickly go through some, I'll touch on what they are and some nuances for each 4 of them. So, by the way, the term ACID was coined in 1983 by Theo Harder and Andreas Reuter, right? You might all know, no prizes for guessing this. Atomicity, consistency, isolation, and durability. So, while I said a few slides ago that the transaction semantics across databases from system R to a MySQL or Postgres, Oracle, or SQL Server have remained pretty sort of similar in our understanding, saying, you know, this is what transactions are and all. Transactions are actually a slippery slope. If you look at one database's implementation of transactions, it's very different from other databases' implementation of transaction. And as a consequence, the guarantees they provide you are very different, right? The devil is in the details, right? When you write your application, you really need to know what you are looking for, what this database will provide, and where are the edge cases that you need to handle well, especially in the distributed database settings or distributed application settings, right? And if they are stateful, even more so. So, I think today, ACID has become more of a marketing term, in my opinion. And this opinion is derived from Martin Kleppmann's opinion. So I followed a lot of his work. I even fund his research in a small way. So what he says is, ACID has now become a marketing term. Every database vendor who wants to sell his own database says, you know, I support ACID and all. But if you look under the hood, you look at implementations, exact guarantees it provides, what trade-offs it has chosen to cater to the market it is targeting. It's not binary, right? So like I said, the devil is in the details. And then sort of, I also encountered something called base. Now, I'm not going to get deeper into it. I'll stick to ACID. But the point I'm trying to drive home here is, now transactions have also gone from ACID to base. And it's only confusing people on what are transactions actually, right? Or maybe there are more cases or something. But to me, what is base? Is it transactions because I want to market it as a transactional database? And then I say that it's not ACID, but then it's base. So having laid that context, let's very quickly go through ACIND, atomicity, right? On the right, you see that I have put a sample. You have atomicity saying, I will guarantee you that all these statements in the transactions will be executed, or nothing will be executed, right? That's something that people would definitely remember. And then typically, you will have begin and commit in the beginning and the end. Not in all the databases though. We will see in the DynamoDB case, when you look at the transaction API, the begin and commit things are not there. It's still transaction, which is okay. Different API. But what we are trying to say here is, if you go through the sort of statements in the transaction, insert, select, update, maybe those could go through. Delete and insert cannot happen. So the database has to have the ability to undo what it was doing, right? After the third statement there, the update one, right? So you can abort the transaction. That's what the database guarantees. Under the hood, it has to have the ability to undo what it did via an undo log or something. But if you look at it from the application point of view, what the database is trying to say is, I will undo whatever I did, so there was no effect, meaning in the application, you can very easily, mindlessly go and retry the transaction. But do you think retrying transactions are safe? Any opinions on that? Like completely safe, not safe, some scenario, some edge case? Anyone? Just take a guess, something. We'll be very few people, so we can have a more conversational one. Right, that's a good one. Anything else that you can think of? Okay, yes. We will see a few cases. Yeah. So, yeah? Okay, yeah, makes sense. But I'll also present a few cases to drive the point home. Right, correct. No, my question is, if the transaction fails and the application retries the transaction a couple of times, 5 times, whatever it decides to, is the retry going to be a problem, right? That's a gray area to me. It could be a problem, it could not be a problem. And then there are some nuances that I found while I was researching, and I'll present those. So think of this case. So there is a client, and then there is a database server. The database server actually executed all the statements in the transaction and did a commit. While the commit was getting from the database server to the client, the network snapped off. The database committed, but the client does not know that the database committed, right? Now, if you have designed the transaction in such a way that your transactions are idempotent, right? Or you have some way to dedupe your data, right? Then it's okay. If that's not the case, then your database could end up in a slightly different state than what you had thought of, right? So, idempotency, people are clear, or do you want me to take a quick example? I mean, with a small group, we can be conversational. Yeah. Okay. So idempotency, what it is trying to say is, let's say for the primary key 10, there was some value saying 100, and I want to change it to 110. One way to say is, whatever it was, make it a plus 10. And the other way to say it is, where the primary key is 10, make it 110. If you do the second one twice, there's no problem, right? If you do the first one twice, then 100 to 110, and in the retry you go 120, right? So that's a problem. So as an application developer, you need to be cognizant, right? In my experience, I think if you can keep idempotency, it makes things quite simpler, right? And these are quite nasty bugs. Can I get some help on this? The laptop? Yeah, okay. This is good. Thank you. The second case is, when you're writing your application, think, what if the transaction could not be executed because the database was overloaded, and you are trying to retry the transaction again and again, right? You're only going to get worse with your database, right? Database server. So you don't want to retry when the database is already stressed. Third, There are two kinds of errors really, right? When I write an application, I think in these two ways, try to at least bucket the errors in these two ways. There are some transient errors and there are some permanent errors, right? For instance, if you are trying to delete a row which does not exist, it's a permanent error. You can keep retrying, it will never succeed, right? On the other hand, there are transient errors, maybe some situation where there is some other transaction trying to update the same row, there is some timeout, some network issue, like the point was brought up earlier from Vinod. I think in that case, you can retry the transaction and it will go through, right? So you need to, as you write application, think what are the transient errors, what are the permanent errors. Try only in case of transient errors. In the permanent error, don't do retries, right? And this is not with databases, this is general. What if the transaction had other side effects, right? Generally, when you write an application, you do some transaction in the same method, you put, maybe you send an email, you execute a trigger somewhere on the database or something like that. If something like that happened, the transaction executed, the application doesn't know, so the application will retry the transaction and that side effect will be happening again, right? That could be a problem when you are designing your application. The last case that I will mention is, think of this. Now again, the database tried to commit the transaction, it could not execute the transaction. The client has to retry now, but the client got crashed. You lost that state of the data. You actually lost data. We are sort of very, very concerned about data that we have written in the database and we got lost. But it's probably the same effect if the application had the data and it was trying to write, and in the event of retrying before that, the client crashed and the data was lost, right? So what I'm trying to say is, although atomicity looks like something where the database guarantees that I'll either do everything or I will do nothing, so you can safely retry. It's again a gray area when you are designing your application. So we have to be cognizant of it. Next, consistency, right? This is the example that I read first in the book, right? There are two accounts, account A, account B. You have $200 in account A before the transaction, 100 in the other account. You take 10 rupees from this account, put it in that account. So this account A becomes 190, account B becomes 110, things like that, right? So this is consistency that ACID guarantees. Now, the problem with consistency is, it's the most weakly defined part of ACID, in the sense that database itself cannot guarantee consistency. So this, and by the way, this consistency, this ACID consistency is very different from CAP consistency. That's a different subject itself, right? So if you write your transaction in your application, both of them wrapped together, it's a different thing. If you make sort of deducting sort of 100 from account A and deducting and adding 100 to account B as separate transactions in your application for some reason, then you are losing that invariance, right? So the point I am trying to drive home in this slide is that your database alone cannot guarantee you that consistency that you are looking for, trying to make the invariant true. So trying to sort of make that certain statement true about your data is also a shared responsibility with your application. So although we say that ACID will guarantee you consistency, that is also something where application have to share some load. Isolation, right? Another thing that we read sort of saying, there is some data, there's some table, in some database, and you are doing two transactions. Let's say there are two different clients trying to do some transaction in two different threads, two different API calls, whatever, right? So what ACID guarantees you is that the database will guarantee you that the effect that T1 and T2 executing concurrently will be same as if T1 happened first, done, then T2 happens, right? And the gocha we are going to look at here is, now when you read it in the books, it seems like serializability, right? The when you get to the implementation details of transactions in databases, you will see that serializability is actually going to incur quite good performance penalty on your database. So typically, even if you look at your Postgres, MySQL and all, so they will implement snapshot isolation, which is a much weaker guarantee than serializability, even though we are conditioned into thinking with academic books and everything that isolation means what serializability is, right? And finally, durability, right? If I ask here, most people I think would know what is durability. Durability basically means that once the database executed the transaction, you will not lose the data. Again, there is something to think there. So for a single node database, for instance, what will you do? Like the database will write it to disk. That's what durability it guarantees. If you have a distributed database, meaning multiple nodes, you have to write to multiple nodes, all of them or most of them persist, and then you say in this distributed database, the transaction has executed and committed, right? So we'll not lose it. But then there is no perfect durability, right? It comes with a clause within these boundaries, right? What if in the single database node, what if you have this database, you wrote it to disk, at times hard disks can crash. You can lose data even from hard disks, right? What if you had a distributed database, maybe in the same data center on same zone, and there was some natural disaster and that whole zone got wiped off. You're thinking of humans and other things, not your database servers there. You have lost data though, right? So although when first read durability, we think that the database will guarantee that it's always there. It's not always there. So you need to know what always means to me as an application developer. So we looked at ACID. Now we will go a little bit internals. We won't go very internal looking at everything because that's too much given the time we have. But if there is enough interest, I can do another talk somewhere. But basically, when you are trying to implement a transaction, you are trying to fight between two things. One is you want to execute as many transactions as you can given a unit of time, right? Like the throughput number of transactions per second has to be really high. That's what you are trying to do, right? On the other side, you have to be under this limit that you have to only do so much so that you can preserve the ACID guarantees. As long as you are preserving ACID guarantees, you can do things concurrently and it's okay, right? If you do the concurrency bit in slightly wrong ways, you will have read and write anomalies. This whole isolation levels, multiple isolation levels and all, in my opinion, is a little bit of a mess, right? It's not easy to understand. At least I don't feel very comfortable. I remember each one of them, and when I write an application, I very consciously think which one do I need and everything, but you should, right? I try to do that. But so isolation levels, what it is trying to tell you is basically choose between these two. To what extent you are going to push correctness, in what conditions you are going to compromise, and maybe the application can take care of some of those cases. Like in DynamoDB white paper, if you go through the white paper, they very nicely articulated how for them this thing makes sense because some of the heavy lifting can be, some of the failure scenarios can be handled by the application also. And concurrency control on the other side, improving efficiency, there also has to be done where you lock certain things and stuff. There is optimistic locking, which is in the case of DynamoDB. There is pessimistic locking, I think, in the case of Postgres and all. So the ones that try to be really consistent. So in the single node databases, right, or single master databases, the responsibility of providing ACID guarantees lies with storage engine mostly. So if you look at this diagram, this is a snapshot I took from the other talk I did at Open Source India, where I covered all the different layers in databases. You have this transport. So how does the client talk to the database or database servers talk to each other? Query processing, if you fire an SQL query or any query, it has to be parsed and everything, optimized. Execution engine, do you execute in this place or spread out some parts everywhere or push it out to other people only. But storage engine is what is going to take care of your transaction. For the other things and all, you can see this other talk. I'll leave the YouTube link at the end so you can watch that talk if you need, or just ping me, I'll send you the link. But in the storage engine, you have all these components called transaction manager, which will coordinate the transaction. As we go ahead and look at different ways of implementing transaction, we will talk a lot about it. So I'll reserve that for now. Log manager, like you would guess, will take logs and save the critical sections so that you are able to execute more transactions concurrently, making sure that your consistency guarantees are fine. Buffer manager is basically your managing your page caches and all, right? So in the database, even in a Postgres or MySQL, when you are executing transactions, you are basically keeping the state of the database, some of the latest state in memory only for efficiency, while you have to persist something because you promised durability. You do that writing to write ahead log, right? Postgres, for instance, bypasses OS and does a ODirect flag on the operating system itself. So if you fail or crash, the last bits which are only in memory, dirty pages, and those are not flushed to disk and all, those can be recovered from what you have in the write ahead log. That's the responsibility of the recovery manager. It's a very interesting thing how buffer manager and recovery manager together work to get efficiency as well as durability. I am really bad with this. Yeah, okay. Maybe not so bad now. Moving over from single node databases to distributed databases, and how do you do transactions within them, right? So the problem is, what if there are multiple nodes, each hosting database servers, and you are trying to drive a transaction across these nodes? An easy guess would be send a commit request to all of them, or ask everyone to execute the transaction independently. Do you want to take a guess, a quick guess on what could go wrong? Sorry? Right, true. Other points? Any other thoughts? Perfect. That's the first thing I'll show up. Yes. Any other thoughts? Okay, so we'll come through one by one in stages. So, like the gentleman said, if you ask everyone to just go and execute transaction independently, then there will be some success and some failures, right? Now, if you leave it like that, the database is going to be in an inconsistent state. So you can't leave it like that, right? What if you go and tell, so the once ticked correct, success, what if you now tell them that, hey man, just go and abort those transactions? The problem is, database guarantees you that once you commit, you can't revoke on it. So that's a problem, right? The other way to do it is, if we had that transferring 10 rupees from one account to another example, we can put a compensating transaction saying, now to revert that, I will put another transaction where I'll do the reverse transaction, right? So I sent 10 rupees from here to here, I'll send 10 rupees from here to here. The problem is, do you keep that logic in the app or do you keep that logic in the database? For database, it's too much to understand your application and put that, right? Maybe you can keep it in the app, which is what roughly, if my memory serves right, Saga pattern does. You can read through that. I'll omit the details there. But if you're trying to do a distributed transaction across databases, across applications, then Saga pattern comes to help there. But the final way is ask people first, right? Saying, hey, can you commit? Can you commit? Can you commit? And if you say yes, by the way, you have to promise me that you are not lying. You will really commit if you said you will commit, right? And that's what we explore in this first formal method called atomic commitment, right? So let's say I had 3 database servers, like I showed in the diagram earlier, and everyone has to vote saying, yeah, I did my pre-checks and I'm fine to commit. And if everyone says, yes, I can commit, and they promise that they will not going to go back on their promise, then I can go and commit, right? And if there are some failed processes, ultimately they have to reach the same conclusion. That's the promise we are looking at here. This will not work in the case of Byzantine failures, which means you're not going to lie. You're not going to fool me saying, yeah, I'll commit, and then you're like, you changed your mind, right? Or you're not going to form groups saying, we will try to together game the system, all of that. No, it's like independent systems. I talked about transaction manager. It's also called coordinator. So that is the one which will coordinate all of this. And atomic commitment actually quite popular. You might have mostly used one of these databases, right? MySQL, Postgres, DynamoDB, Spanner, or Kafka. All of this, in some form, use atomic commitment, right? The same thing represented diagrammatically. You have a coordinator. A coordinator could be a separate library or executable, or a coordinator could be within the part of your database server itself. So any database server that gets a request to do a transaction, that will coordinate with other database servers. So it could be a coordinator, or it could be your database server 0. You're writing data. Then you are saying, hey, can you promise me that you will be able to execute this? Can you promise me? And if everyone says yes, then you are fine. Then you go and ask everyone to commit, right? And we will go one layer deeper to see how that happens. But formally, these are called prepare phase and commit phase. That is why this is called two-phase commit. Two-phase commit is very well adopted. In MySQL distributed transaction, for instance, they use this. In Spanner also, in some way, they will use this. In DynamoDB also, they will use this. So across a lot of databases, right? SQL databases, NoSQL databases, cloud databases, open source databases. Quite good adoption. As a coordinator, if I asked everyone to prepare, they said yes, and I decided to commit the transaction, that's my decision now, then I have to write that decision in my log file. I persist it, right? Because what if I got all the prepare, and before I could send them commit, I crashed, right? So that's why you want to write your decision in your log. So when the process comes up again, or another process comes up again to serve the transaction coordination, then it can look at the decision in the log and talk to other folks, right? Or you talk to some folks, you couldn't talk to some other folks, or something like that, right? And by the way, if you, yes, please. I'll get to that. Very good question, right? So just one bit and then I'll get there, right? So the coordinator got a prepare from everybody. It could not write to the log that I want to commit and crashed there only. When it is recovering, it will go and look at the log, like your write-ahead log recovery, right? It will look at the log and see that it did not make the decision. It doesn't know that everyone prepared and everything, so that transaction will be aborted. But if it has written the commit and not told everyone to commit, then while it is recovering, it will try to talk to everyone saying, hey guys, you promised to do this transaction, so now go ahead and commit this transaction, right? Coordinator can change, but it has to still stick to that log file. DynamoDB does that, right? But it's complicated. Like, I don't think your Postgres or MySQL will do that, right? Has to. Unless you have a central logging system for the coordinator and this process just talks to it, so this goes down. You have another instance in Kubernetes pod which comes up and talks to the same log or storage system, then it's okay, right? Otherwise, as long as you stay committed to that log file, right? That's why that there is that log file. And now getting to your question, right? If as a database server, a participating database server, I said, yeah, I'll be able to commit it. I can do that. And then the coordinator decided that I will execute the transaction, ask everybody to commit, and I went down. When I come back, I have to stand true on my promise again, right? So I have to execute the transaction and commit it, right? That, I think, answers your question. But, okay. Mm-hmm. Right. So when it comes back, it has to do that commit now. That is the guarantee the database server provides. Correct. Yes, yes. Oh, yes, yes. So if the coordinator has written, I want to commit this, I have seen everyone's vote, I want to commit this, then everybody has to commit. If at that point the coordinator goes down, then transaction will be hung up in all the database servers. Right? This is very subtle. It depends, right? If the coordinator in its log did not write commit yet, even though it collected the acts in prepare phase, then it will recover when it comes back. It doesn't know if I looked at everything because it did not persist a decision. But if it persisted that decision of I want to commit, then when it comes back, it will commit. And if the coordinator takes 5 minutes to come back, this transaction will be hung up. Like we had the suggestion that mysql also times out and everything. Those are also there. But in general, in the two-phase commit, if the coordinator goes down, the transaction is stuck across database servers. If some database server is stuck, it has to deliver on the promise that it had made, if it is asked to. Right? So commit is also an act sort of managed by coordinator. Yeah, thank you. So, yes, please. Mm-hmm. That is a choice that the application can make. The application can say that I will only try for 60 seconds, then I will consider this is not going to happen and I will retry. And for retry, I mentioned some cases, so you have to be cognizant of those. Right? I think you came a bit late, right? So I'll send those slides, the recording will be there, right? But that's a decision that application has to make, whether it wants to retry or what it wants to do, right? But application could retry there. So this is just the, This is just the diagram when the coordinator crashes. I think I explained that pretty deep. Any last questions there? And then we will move. I have a feeling I've taken a lot of time, but it's okay. I think this was really the important bit. Any other questions, or we can move? Okay, let's move. And I'll be available for a bit for the questions later. So as I think we have discussed most of this, if the participant says yes, it has to commit. If the coordinator decides once and writes its decision, it cannot go and revoke that decision. If the participant said yes and didn't hear back from coordinator, wait forever. Coordinator must persist decision before it sends participants. If no commit record persisted in the coordinator log, abort and recovery. I think I've explained all of them. So now we've seen that there are a lot of failure points in two-phase commit, right? It's a blocking protocol, right? So to mitigate that, there is a algorithm called three-phase commit protocol. Unfortunately, that's not very well adopted. Like I said earlier, MySQL, Postgres, DynamoDB, Spanner, all of them implement two-phase commit. And we will look at the architecture, how they try to get around the problems that we just mentioned, right? But two-phase commit is quite good. Three-phase commit is a little bit difficult, and there's a lot of chatter that happens. There's already a lot of chatter here, right? This guy has to go ask everybody to prepare, then collect that, then write that, and then ask everyone to commit and everything, right? So there's a lot of extra things already that happens. And by the way, if you look at the numbers, there is a report where they say that if there is a single node database server or a single leader database server, then you are 10x more efficient. Yeah, 10x more efficient than doing the distributed transaction. Obviously, writing that extra fsync, doing all that, the coordination in network is going to cost you. And we will see how Dynamo decides, Aurora decides completely against it. So what are some other choices, right? Very quickly, this slide is a bit dense, but in the interest of time, I'll go through quickly. But if somebody is interested in discussing these things, I am going to love it, right? We can have this discussion. So for instance, MySQL or Postgres, in default, they have asynchronous replication. One guy will execute transactions, write it in the log, write-ahead log, and that write-ahead log will be shipped to the follower, not shipped, pulled by the follower from this side. There's some protocol there. We can, again, discuss that after the talk if you are interested. But that leader, so there are three databases. There's a master and there are two followers. They are asynchronously replicating. How do you select the leader, right? So who is going to coordinate transaction how? You moved that part to now. Who is going to be the leader? So you have not solved the problem. You are still going to have the problem in another place. But then who is the leader is a less frequent question. Who is going to coordinate and how is a more frequent question, right? Transactions happen all the time. So manually select a leader means if the leader goes down, somebody has to come and manually select the leader. If automatic selection, then you have a few choices, right? Zookeeper is actually very popular. It is used by a lot of people to decide who will be the leader. Then there is Raft implemented in etcd. Etcd is the component behind Kubernetes, by the way. And Kubernetes, I think you would know that it is quite well adopted. So etcd is quite popular. Paxos is actually quite famous for being difficult to understand, right? So not a lot of databases use Paxos. Spanner will use Paxos. We will see that at the end. But we'll not go very deep. You can go through the Spanner white paper to see the details. And there is another way where you can have a sequencer. There's a database. This algorithm is called Kelvin. And this database, FaunaDB, implements that algorithm. So you can have a sequencer, central sequencer, which will sequence the transaction. And every database server has to stick to that sequence. The point is, if all of us start at the same state, and we do the same transactions in the same order all the time, we will be eventually consistent. Correct? The other thing you can do is, all the problems that we were discussing here, the questions there, some pretty interesting ones, where because the coordinator fails, or some participating node in that whole prepare commit, that fails, right? Spanner takes care of that very nicely. Because what they do is, instead of single nodes, they make a group. Let's think of a shard, or they formally call it Paxos group. So one group where there are leaders and followers. The leaders of these shards will do the two-phase commit. One leader will be the coordinator, and others leaders will participate as participants. And we'll look at Spanner again. Let's get to the transactions in modern databases, right? And I will pick 3 databases. How many of you have tried Amazon Aurora? Quick show of hands. Okay, we have some numbers. DynamoDB? Nice, nice. Spanner, anyone? Spanner, CockroachDB, YugabyteDB. Oh, okay, I can talk confidently about those at least. Fine. So Aurora, what it does is, you know the regular MySQL and Postgres and stuff. Aurora is actually a very novel architecture, and they claim that Aurora on MySQL is 5x more performant in throughput than regular MySQL, and 3 times more in Postgres. And how do they do that? It's actually very interesting. If you go to the Aurora white paper, it's some 6 pages white paper. It's very nicely explained there. Basically what they do is, they keep the database server as it is for compute side. For the storage, all that data storage and write-ahead log storage and all, they have a custom-built multi-tenant storage service, which expands as you need more storage. And this is all custom-built using their own services like DynamoDB for some storage metadata, S3 for backups, and there is some. So they very well limit the number of things that should happen synchronously in the foreground, and everything else will happen in the background. Those are done by workflow service. And the storage service actually, so this storage part of the MySQL or Postgres, they rip that out and they put their own storage service. They use the database functions from the compute side from the MySQL and Postgres kinds of databases. So service-oriented design and very nice segregation of compute and storage. So you can scale them differently. So when I talked of segregating database compute and storage, the compute side will do these things: query processing, transactions, locking, page cache management, undo management, and all of those. The storage fleet will do redo logging, materialization of data blocks, like where do you write and how do you balance and all those things. This is, in fact, segmented auto scale out storage architecture. Garbage collection, meaning if you updated some rows, the old versions of those rows, right? Backup and restore of the database, because all of the database obviously remains there, right? So this is how they sort of separate the methods. I will really encourage you to go through the Spanner white paper. Again, in the interest of time, I will not go very deep, but let's take an example, right? So what Aurora does is, it writes your data in the database across 3 availability zones. Every availability zone, 2 copies. So 3 availability zone into 2 copies everywhere, 6 copies we will try to write in a typical setting, right? So V equal to 6. 6 votes is what we are looking at. For a write, 4 of the nodes have to vote for write, saying I am fine to do the write, I'll do the write. For reads, you need to have at least 3 votes. I think, and the one thing I skipped, which is there in the header, is Aurora says that two-phase commit is very chatty. In the abstract section of the white paper itself, they claim that in the cloud-based infrastructure today that AWS manages, storage and compute are not the problem. The problem is the network. We have to really optimize for the network, right? In this whole distributed setting. And two-phase commit is very chatty. We saw all that prepare phase, commit phase, and all of that, right? So they get rid of all that. They say, I will go with quorum style of consensus. For 6 copies, 4 votes for write, 3 votes for read, right? And that is configurable depending on how much write throughput you want, very high write throughput or very high read throughput and stuff like that, right? So number of read votes plus number of write votes has to always be greater than the total number of copies you are trying to write. This is because when you are trying to write, so when you are trying to read, you should have at least one of the ones which have voted for the write, right? So I wrote 6 copies. I wrote at 4 places. So out of 4 places, out of 6, if I choose any 3, at least one of those 4 will come there, right? And when I get all the responses, I will look at the responses and see which is the most latest one, right? And I can update the other ones at that time or put a asynchronous job to make the others eventually updated and all that, right? And the other one is when you're trying to write, you have to write on, so write vote is 4, right? So you have to overlap with the last write set. If you're trying to write in the database, you want to make sure that the just previous write, I have got data from at least one of those. And I'm writing on the most updated one. I think I went through that a little bit faster in the interest of time. But again, we will discuss that in the Q&A section or after the talk. DynamoDB is a very, very interesting database. I come from the MySQL world. I was employed by MySQL, and I knew that very deep. So I really appreciated consistency. And if you remember the beginning of the talk, NoSQL camp, SQL camp, I was pretty much SQL camp as a kid. DynamoDB actually opened my eyes to the NoSQL world. They, in their white paper, put it very, very nicely how, given their requirements on the Amazon e-commerce app, DynamoDB makes perfect sense for their business. DynamoDB, if you look at the cap, prioritizes in the event of failure availability. Postgres and MySQL and all, or Spanner, CockroachDB, Yogabyte, I think those also will prioritize consistency. DynamoDB, a popular example is the shopping cart in Amazon's website that is powered by DynamoDB, right? So the guarantee that they give is that I want to be always available. You will always be able to add stuff to the shopping cart, right? And which obviously works wonders for their business. So they don't use two-phase commit and all that. They use quorum-based consistency, slightly weaker consistency, but high availability is what they try to do. So the promise they give is, you will always be able to write to the cart, shopping cart, and you will never lose the data if you wrote something there. But what can happen in really bad cases is that you deleted something from the cart and then added something and all of that. You confuse the system because the servers were going up and down. Some deleted item in the cart can sometimes reappear. But that is easy for them to handle, right? They sent you something that you do not need, so you can return it back. So that's how the use case for which that database works dictates the choices that it makes, even for transactions, right? They use something called sloppy quorum and hinted handoffs. Hinted handoffs basically is trying to say that, you have a circular ring with a lot of servers on the ring. There is a specific guy which is asked to execute the transaction. Let's say you want to write 3 copies. Then on the ring, this guy which got the request plus 2 just after it on the ring, those 3 will execute the transaction. If one of them is down, then the next one in the ring, that will execute the transaction, store the state, and as soon as the other guy comes up, this hint will be transferred to this guy that you're supposed to get some data that is stored with your neighbor, so that will get it, and this guy will get rid of it, right? So that's what hinted handoff is. You hint that there is something that you have missed while you were down, and you hand it off, and then go with the promise you made to write only with neighbors. So there are no holes. Again, this NRW I use from the paper itself. N is the number of nodes that you are trying to write the data to. R is the number of votes you need for a read. W, the number of votes you need for a write, right? R and W have to be greater than N. Then we have seen in the previous slide also, VR plus VW greater than V. Typically, so DynamoDB in different applications, like shopping cart will run its own DynamoDB. Some other Amazon service will run its own DynamoDB, right? So they can play with these values of NRW, how many copies, how many read votes, how many write votes, they can play with that. A typical value is 3 copies, 2 votes for read, 2 votes for write. That works well for them. For very high read performance, what you want to do is, if you have some writes for very high read load, then you write everywhere, all the time. So W equal to N. Write votes is same as number of copies you want to write. So you can read from anywhere. R can be 1. So very high read performance. If you want to optimize for write availability or throughput, then W equal to 1. So you got at least 1 vote, you go ahead, right? Maybe some stale data you will read sometimes, but it's okay because you want to really go for write traffic optimization. So here is an example. I promised you that the DynamoDB folks don't have a begin and commit all of that. So I'll show you quickly how their transaction API looks. Again, this is a schematic from the white paper. I took that snapshot and then I had made some notes on the white paper. So that's the photo I have here. So you see that somebody is trying to purchase a book. You have to do 3 things, right? You have to first make sure, look at the customer table. Customer exists, genuine customer, registered customer, inventory. So the book has to be there in the stock. And orders, you have to put in the order table that this order is going to be done. This is the book, this is the number of copies and everything in the orders table, right? So you have 3 statements. You made those 3 statements. This is the DynamoDB client APIs. Then you make a transaction write item request with the red, green, and yellow underlines you see, right? Those are the 3 objects there in the transaction request API. And then you ask the client to execute the request, right? So this is how the API looks there. And there is good reason why they made this API and not the regular begin, commit, and all of those. I have put a link to the blog in the reference section. This is a graphic from the same blog. The link is at the bottom. I'll also put it in the reference section. But what they're trying to do is, here is the app. Let's say shopping cart app in Amazon.com. So shopping cart app will ask the request router to execute the transaction first. Request router will look at the request, authenticate, authorize, and all of those things it will do. Then it will go to the transaction coordinator. That's the same coordinator that we looked at in 2-phase commit, right? This guy will ask the orders table, inventory table, and customer table, everyone, to confirm that they vote yes for the transaction, the prepare phase, right? If everybody says yes, they will go ahead and commit the transaction. If some say no, then they will not commit the transaction. As per 2-phase commit, right? Quorum is different, maximum people and everything. And we talked about writing the decision in the coordinator's log. What DynamoDB does is, for the last 10 minutes, they keep that log, so log doesn't grow very big. But every time you execute a transaction, so when you're trying to execute a transaction coordinator will attach a transaction ID in the header. They will put that ID in the log, which they call ledger, right? And within those 10 minutes, if you're trying to retry the transaction, then it will see in the log that ID already exists, right? So it will not retry. Pranav has asked me this question about, can the other process come up? That ledger survey is centralized. So in this case, if this coordinator goes away, other coordinator comes up, then it can look at the same ledger and restart there. Spanner, finally. Spanner is one of the first distributed SQL databases and was the inspiration behind CockroachDB and YogaByteDB, right? There's more history there, maybe of the records we can talk there. So some people from Spanner are some people who started coordinator, Cockroach and all that. So Spanner is your normal tables, columns, rows. Values are versioned, right? So when you commit, the version of the value, there the timestamp is written there. That's how they version it. Supports SQL. It's not ANSI SQL. It's slightly different SQL. I did not put that picture of how the SQL looks in the interest of time, but you can again go to the white paper. It's a little bit difficult, so I had to read 2-3 times when I first read, but it's okay. The application is allowed to have very fine-grained controls on what it wants from the replication layer. So it can say what data centers it wants to write on, how many replicas, how far these replicas should be from each other and everything. And using that, it will manage write latency, read latency, durability, and all of that, right? So that decision is there in the client API. Clients will automatically fail over between replicas, and they will also make sure that they have these zones, and between zones and all, or even servers within a zone, within them, there will be a service, placement driver service. It will move data between them to make sure that the load is balanced across servers, right? We'll take a quick look at the diagram, right? This is again a diagram from the white paper. I have put some notes around it. This is zone 1, zone 2, zone 3. Zone master, when there is data, it will assign one span server where the data should go. If some client comes for reading, location proxy will tell where it is going likely to find the data, so you can go there and look for the data. You can have hundreds to thousands span servers in one zone. This universe master is basically trying to give you status for the whole system, every server and everything, so you can debug using that. Placement driver is automated movement of data across zones within minutes, right? Spanner is actually built on top of big table, right? Big table is basically something that introduced tablets. It's a huge key value map, right? Huge map of key values. Storage is their distributed file system. Paxos is the one that keeps states for replication, so hosting state machine for replication. All those nodes, all those are put as the notes in the next slide, so you don't have to remember everything. But like I described when we were talking two-phase commit, right? If the coordinator goes down or one of the ones that has to vote goes down, there is some problem with two-phase commit. So these guys use two-phase commit. But you see the red one, that is one Paxos group. Think of it as one shard. The blue one is another one, green one is another one. If this leader goes down, the replica will be promoted to become the leader. And the same in the other two, right? So they're trying to make sure that way that there is high availability across the ones that are voting, right? So they will not go down easily. And if you are trying to do a transaction that only deals with this Paxos group in the blue box, no two-phase commit. If it is across, then you have to do two-phase commit. Across zones, then you have to do two-phase commit, right? So by making sure these are available, by having failover and everything, they make sure that those who vote or those who collect the votes, coordinator and everything, they don't go down. So that's how they try to go around the problems with two-phase commit. That is mostly all I have. So these are two books that I have read at least 4 or 5 times. And a lot of the content is opinionated based on my readings on those books. But I also have gone through all the white papers. And a lot of these diagrams are from the white paper. And then there is this last blog that I mentioned where I think an engineering manager, senior engineering manager from DynamoDB team has written a really nice blog on the DynamoDB transactions.
Hey, thanks for joining us for this insightful session from Mydbops Open Source Database Meetup 15. We hope you found Shivji Jha's presentation on modern database complexities valuable. We will be releasing videos featuring our next 2 speakers soon, so stay connected with us by subscribing to our channel for more informative content. We invite you to join us at our next event to continue learning and networking with professionals in the field of open source database management.